In the previous video, we saw how to draw ray diagrams for spherical mirrors. And now I'd like to go and be able to extend that to get quantitative. So I'm going to start by drawing a case 1 situation, which is where the object will be located outside the center of curvature. Now, so here's the focal point. Remember, the center of curvature is 2 focal lengths away from the mirror. And so in a case 1 situation, our object will be located. There we go. Our object will be located outside the center of curvature. So remember, when drawing a ray diagram, we always like to use the 3 special rays. All right, which are the paraxial ray, which we remember gives us a ray that reflects out through the focal point. The focal ray, which gives us a ray that reflects back out parallel. And then our truest, bestest friend is the central ray, which comes in and back out at exactly the same angle. So the height above is the height below where the object is located. All right, we're not going to be interesting ourselves so much in the central ray here, or the paraxial ray for that matter, but it is worth pointing out that there is one more ray that is useful. I tend not to make a big deal of it because it's only useful for mirrors, whereas the 3 that we've done so far are useful for lenses as well when we get to them. But it turns out the 4th most useful ray is the ray that goes straight through the center of curvature. And this is because it will strike exactly down the normal right here and bounce straight back out on itself. So we're mostly going to be interesting ourselves here actually in the central ray, in the central ray, and this special ray that goes through the center of curvature. So I'm going to gloss over the derivation because I don't think it's particularly instructive. But what you can do is you can observe that this triangle here that I'm highlighting in lime, oops, let me locate my image here. There we go. Is similar to this triangle here. Again, it's made with the central, so object, central ray, optical axis, image, central ray, optical axis. Because angle in equals angle out, and these are right angles, these 2 triangles are similar triangles. Similarly, let me highlight it in some sort of purple here. This triangle right here, made by the object in the center of curvature, is similar to, this, there it is, to this triangle right there, made by the image in the center of curvature. This angle is the same by alternate interior angles. That's a right angle, that's a right angle, so they're similar triangles. And you can see that I drew this terribly. Let me relocate my image to try to make it a little less awful. There we go. And I'm just going to freehand this line too, because apparently I just did a terrible job of drawing it. There we we go. So in, out, like that. All right, so anyway, the two lime green triangles are similar triangles. The two purple triangles are also similar triangles. So if you set up a bunch of proportionalities from these triangles, you will obtain three results. The first result that you will obtain is that the focal length is equal to 1/2 the radius. You will also obtain that the lateral magnification, and I'll explain the minus sign in a second, is minus the image distance over the object distance. So let me just dimension those in. So this is my object height, h. That's my image height, h prime. This is my object distance, s. And this is my image distance, s prime. So you'll note that the magnification, my bad, s prime. So we will note that the magnification, which is lateral magnification, which is h prime over h, when you play with the similar triangles, you will also get as minus s prime over s. And finally, you will also obtain that 1 over s plus 1 over s prime is equal to 1 over f. Now, pretty much every book will call this a mirror equation, but I will call this the most useful equation in optics. That's because when we do this whole exercise again for lenses, we're going to get the exact same equation when we do lenses. Now, this was only done for a case 1 situation. In order to do this rigorously, you have to do it again for case 2, case 3, and case 4, and each time you get the exact same answer. Now, this only works if you agree on how to assign plus and minus signs. And there are actually multiple ways you can do it to make things consistent, but what is adopted by most optics texts and most physics texts is what is called the left-light convention. There are other conventions out there, so if you're looking at just some random book, you'll have to take a look and see what they're using. But let me just make a quick table here, and then we'll get into it. So plus, minus. For focal lengths and radii of curvature, it's positive if the mirror is converging and negative if it's diverging. I'm not motivating this. I'm just saying if you make this choice of sign, the collection of equations that I give you works out. For your lateral magnification and also for your object and image heights, if the thing is upright, it's positive, and if it's inverted, it's negative. And then for object and image distances, if the object or the image is real, it's positive, and if it's virtual, it's negative. So the idea of this convention is that if something is where the light is, it's positive, and if it's where the light ain't, it's negative. So for instance, here, the center of curvature here is where the light is. The light comes in and it reflects back out. It'll pass by the center of curvature, so the center of curvature is where the light is. With a diverging lens, the center of curvature would be over here. A convex mirror, the center of curvature would be over here. And so the light would all be on this side of the mirror, and the center of curvature is over there. So the center of curvature would be where the light ain't, which makes it negative. Similarly, if we have a virtual image, it's located behind the mirror. And so that'd be where the light ain't, making it negative as well. It is possible to have virtual objects. However, those only come up in complicated multi-lens and multi-mirror optical systems that are way beyond the scope of our treatment. So in this treatment, all of your objects will be real objects and will have positive object distances. But be aware, in more advanced treatments, say if you end up designing lenses for Nikon or something like that, it is possible to have what are called virtual objects, where the object distance is negative, but we will not be treating that here. However, if you have a real image like this one here, you can form the image on a screen, but it's also for the images where the light is. The virtual image, remember, is located behind the mirror where the light ain't. So this particular convention, which is known as the left light convention, because you can remember these by it's positive, it's where the light is, and negative, it's where the light ain't, both for this and this, it's a very popular choice. And then upright and inverted, I think that just makes sense. All right. So let's go and try as an example here. Let's say that we have some object located 15 centimeters in front of a convex mirror. So since it's a convex mirror, it's going to have a negative focal length by definition. So let's say it's negative 25 centimeters. So when we're drawing the ray diagram, we'll locate the focal point and we will locate the center of curvature, which will be twice as far away. Let's say that our object is located 15 centimeters in front of the mirror. So S equals plus 15 centimeters. Let's also say that our object height is 3 centimeters. What I'd like to do is locate the image and figure out how tall that image is. So remember, when you're solving any physics problem, the mnemonic is STAR: situation, tools, answer, review. So here you want to draw a ray diagram. And actually, you want to do a half-decent job of it, because drawn carefully into scale, for instance, if you're using a ruler rather than the digitizing tablet that I'm using here, you draw it carefully with a ruler, a carefully drawn ray diagram will be the answer. You can just draw it to scale, measure it off, set up your scale, and that literally will give you the answer, and it is a totally valid way to solve it. But at the very least, even if you're not going to do a perfect job drawing these things, at least go and draw a ray diagram with the 3 special rays. There we go. So paraxial ray comes in, bounces out away from the focal point. Central ray bounces out below as it came in. And the focal ray, remember here, in this case here with a convex mirror, the focal ray will be aimed towards the focal point. Again, if you want to draw dots, not dashes, to help you visualize that, that's totally fine. And it will bounce out parallel. So we can backtrack the reflected rays to locate the image. Sorry, I did something physically impossible there. There, much better. And so we can go ahead and locate our image. Now, first test. We know it's case 4, so it should be virtual, upright, and minified, and that matches our drawing. Secondly, we can look here and see, okay, the image is located where the light ain't. So even though the image distance is something we're trying to calculate, we already know that we should be getting a negative number. Now the other thing we were asked to find is the image height. And we already know just from looking at this that it should be a positive number because it's upright. Okay. So that's our situation. The tools will be the most useful equation in optics and the magnification equation. So for answer, remember you always set everything up as letters and solve for what you need as letters. This will be especially useful when we get to multi-element systems where you're often taking the answer of one thing and sticking it into the identical relation for the next thing. No sense reinventing the wheel a zillion times. So we want the image distance. So this will give us 1 over s prime is equal to 1 over f minus 1 over s. When in doubt, put things on a common denominator. And then we can a little cross multiplication action here will give us that s prime is equal to sf over s minus f. Now, super duper important is when you substitute in the numbers, you gotta carry the plus and minus signs. Otherwise, you will get the wrong answer. So the object distance here is plus 15 centimeters. Now for the focal length, remember, because it's a diverging mirror, that is a negative focal length. So you got to put in minus 25 centimeters. And then S was 15 centimeters again. This will be minus a negative 25 centimeters. We need the minus sign and the negative sign, or this is not going to work out. All right, so this gives us an image distance of negative 9 3/8, so negative 9.375 centimeters. And this minus sign is very important. So it's telling us that the image is located behind the mirror. And we can also see from the drawing that it should be less than 15 centimeters away. And that is indeed the case. It's at minus 9.375, which is inside of negative 15. Okay, so now to get the image height, we can rely on the lateral magnification definition. So that's our lateral magnification is h prime over h, which we found from considering the similar triangles, that was also minus s prime over s. So here, this is going to give me that h prime is equal to minus, and do not drop that minus sign, minus s prime over s times h. So putting in h prime will be minus a negative 9.375 centimeters. And again, you got to keep that minus sign or things won't work out. We said the object distance was plus 15 centimeters. Probably good practice to even carry your plus signs just to be super careful. And then we said the object height was plus 3 centimeters because it was upright. So when we grind this through, we're going to get minus a negative here. So we get an image height of plus 1.875 centimeters, or 1 7/8 centimeters. Okay, does that check the diagram? Yes, it does. It is upright and it is shorter than our object, which is what we expected. Alrighty. So we will be, in the next videos, we will be continuing our explorations of optics. Have a good one.